In December last year, science teams at CERN's Large Hadron Collider reported a hint of evidence of a brand new particle, one that does not fit anywhere within the standard model of particle physics. If true, this would be the first clue of anything beyond the standard model from the LHC. Remember, the standard model is basically the periodic table of fundamental particles and forces that represents our entire current understanding of the building blocks of all matter. Even the incredible discovery of the Higgs boson in 2012 was a confirmation of the final particle of the standard model, and that was expected. If this is real, it may break open entirely new pathways to the research of the fundamentals of nature. So what was seen? Well, let's first think about how particle accelerators, and especially the LHC, work. The LHC occupies a 27-kilometre circumference circle beneath the Swiss-French border near Geneva. A ring of gigantic magnets accelerates protons to up to 0.9999999 of the speed of light before colliding them from opposite directions. The resulting collisions can produce temperatures of several trillion Kelvin. So, a tiny spot, for a tiny instant, resembles the state of the universe at a trillionth of a second after the Big Bang. Under these conditions, protons are obliterated. Their energy is released and reshapes itself into new particles. Many weird particles come out of such a collision, and some are so hopelessly unstable that they decay into high-energy light, gamma rays, before they ever reach a detector. We only know they ever existed because the resulting gamma radiation has an energy corresponding to the mass of the decayed particle. The Higgs boson was found because there was a slight excess in gamma ray flashes at 125 gigaelectron volts above the otherwise smooth spectrum of gamma ray energies. And now there's a new bump at 750 GeV. This suggests a new particle with a mass much larger than anything in the standard model. When it was first spotted, this gamma ray excess was just a little bump, and it could have been the natural result of random fluctuations. Those happen all the time. We wouldn't have heard anything about it except that two completely separate experiments using separate detectors, ATLAS and CMS, both saw the same bump. The significance of the result is still low, at around a sigma of 1.6 for CMS and lower for ATLAS. That's nowhere near the 5 sigma needed for a confident discovery. But particle physicists are completely losing their minds. Over 300 papers have been submitted to journals with a wide range of possible explanations. The broad family of possibilities include 1. Dark matter. There are theoretical ideas for particles that could cause a bump at this energy and would also make pretty decent dark matter candidates. 2. A gigantic neutrino. More accurately, a very massive cousin to the neutrino predicted by supersymmetry, and as yet unproven but pretty popular extension to the standard model. 3. The big brother to the Higgs boson, so a higher energy vibration in the Higgs field. 4. The graviton, a highly speculative particle responsible for the transmission of the gravitational force, but it's not yet even known whether such a particle exists or is needed to explain gravity. Or 5. It's a composite of other smaller particles. Just like the proton is a combination of 3 quarks, this could be a much more massive combination of several quarks and antiquarks. There are links to references to all of these possibilities in the description. There's no point choosing between these options until we verify the results. The LHC is currently offline for upgrades and starts up again in June, following a 2-week delay due to a weasel chewing through a power cable. I kid you not. At that point, the signal will either solidify or vanish, assuming no more attacks by cute animals. Okay, time for the solution to the dark energy challenge question. I'm just going to interrupt Matt here for a second. Sorry, Matt. He's about to go full nerd with the dark energy challenge answer. Before he sends you to sleep, I want to respond to your comments on our Ice Age episode and make this important announcement. On Monday, June 13th, I'm doing a Reddit AMA. We're going to talk about everything space-time. So space and time, really anything physics or astrophysics. We'll also talk about my own research in astrophysics, which is the subject of a recent documentary made by the American Museum of Natural History, linked below. But this is an Ask Me Anything, so the sky's the limit. Wait, it's not even the limit. How's this work? You head over to the r/Science subreddit that morning and post your questions. It'll be the top thread. At 1 p.m, I'll get to answering these and we'll see how much ground we can cover. See you there. Okay, let's see what you guys had to say about our episode on the Ice Ages and the Milankovitch cycles. This ended up being a big discussion on climate change. But that's cool. Astrophysics does have a lot to say on the topic. Bockmaker talks about the connection between solar activity and Earth's climate, and that's something we really didn't touch on in our episode. So it's true that high sunspot activity can increase solar irradiance, and in the first half of the 1900s, increasing activity did increase solar output by about 0.1%. The consensus is that this is much smaller than anthropogenic factors, but even ignoring this consensus, the correlation between solar activity and warming stopped a while ago. As Bockmaker suggests, solar activity is diminishing. In fact, over the past 35 years, it's decreased, while temperatures continue to increase. Xenion341 asks why the current warming trend doesn't quite track the current CO2 trend to the same degree that it does in the paleoclimate record. Okay, well, temperature is following CO2, but the response takes time. Global average temperature has risen by at least 0.6 degrees Celsius, probably closer to 1 degree since around 1900, following the CO2 increase. However, the full effect takes longer because it depends on positive feedback cycles. Reduced ice cover reduces albedo. Warming oceans and melting permafrost add more CO2 to the atmosphere. In the paleoclimate record, we see that an increase in temperature due to Earth's changing orbit precedes an increase in CO2. So the feedback cycle can start at either end, and there'll always be a lag between the two. But once initiated, it doesn't really matter whether the CO2 increased first or the temperature increased first. Each drives the other. Sugar Shakerfi gently asks whether we really can be certain of the broad extent of an effect, given that we can't perfectly accurately model every detail. Now, this is a tough one. The fact is, we don't need to be able to predict with absolute precision to be sure of the trend and the severity of a phenomenon. Weather prediction can usually tell you that it'll be hot tomorrow, but it rarely nails the exact temperature. Similarly, completely independent long-term climate models differ in the details of their predictions, but almost all agree that the current trends will continue. By current trends, I mean the increasing temperatures, more severe droughts, shifting climate zones, reduced ice coverage, etc., whose current effects are very well documented. Sugar Shakerfi also asks why the Mesozoic was so bad. Well, it wasn't. It was great for the organisms that were perfectly adapted to it. Most of those same organisms went extinct due to sudden and massive environmental changes, probably including climate change due to meteor impact. Sudden climate change is very, very bad for ecosystems evolved for the current climate. Okay, back to Mathy Matt for the Dark Energy Challenge answer. Take it away. For the main question, I asked you to figure out how many times the universe doubled in size after dark energy first started to show its influence, and how many times it would double in size in the future before matter no longer has any significant influence on expansion. More precisely, for how many past and future doublings of the scale factor are they both at least 10% of the energy content of the universe? Let's think about a giant box of space that's expanding with the rest of the universe. We call this a co-moving volume. To start with, let's ask how large this volume was when dark energy only comprised 10% of its total energy. So at that point in the past, we know that this equation is true. Right now, 70% of the energy in any volume in the universe is in the form of dark energy. So, 70 parts dark energy and 30 parts matter. Now that looks like this. Back in the day, it was whatever the sum of dark energy and matter was back then. The overall amount of energy in the form of matter doesn't change because matter is spreading out with the expanding volume. Matter past equals matter now for a co-moving volume. But the amount of energy in the form of dark energy is proportional to the volume, and the volume of the box is equal to the length of its sides cubed. We can scale past dark energy according to the current dark energy content like this. And we can just use the scale factor of the universe as the side length of our box. In fact, let's just use R for the ratio of past to present scale factors. In fact, R is actually what we want to find. So our total energy becomes this. Put all of this into our original equation and rearrange, and we get this equation for the ratio of scale factors. Plug in our current 70 units of dark energy and 30 units of matter, and we get that the universe was 36% of its current size when dark energy had a 10% contribution. But I asked you how many doublings ago that was. So you need to double that 0.36 about 1.5 times to get to the current scale factor of 1. You can take exactly the same approach to ask when in the future matter will only have a 10% contribution to the energy in that volume. It'll happen when the universe is larger by a factor of 1.57, or about 0.7 of a single doubling. Add these two numbers together and you get that matter and dark energy both produce a significant effect for around 2 doublings. That's tiny compared to the 100 past doublings that have happened since the end of inflation, and the infinite number of doublings that will happen in the future. For the extra credit question, you were asked to figure out the number of years that this corresponds to. Now to do that, you need to integrate the first Friedman equation over the scale factors that you got for the main part of the question. The answer is that overall, the two influences will be within an order of magnitude of each other for around 15 billion years. Now that may sound like a lot, but we find ourselves right in the middle of this very narrow logarithmic window. The solutions to both parts of the question are linked in the description. If your name appears on screen below me, you got this right and were randomly selected to receive a Spacetime t-shirt. If that's you, email us at pbsspacetime@gmail.com with your address, US t-shirt size, and let us know if you want a Black Hole Orbits or an I'll Science Anything I Want t-shirt. Okay, blah blah math blah. What do I mean when I talk about this being a cosmic coincidence? Is there something about the tipping point between the dominance of matter versus dark energy that makes the universe more hospitable for life? Or should we take this as evidence that our simple idea of a constant dark energy density is wrong? Excellent questions that cosmologists are thinking hard about. We'll come back to both of these ideas in future episodes of Spacetime.